I think at this point, let's talk a little bit about path independence. We saw in the video that we did that when we integrated f of z equals z squared over a few different paths, we ended up getting the same answer. And the question is whether that'll work, whether that's something special to z squared. You know, is this true for all functions? Is this true for all paths? The answer is, of course, no. And so then the natural question is, for which paths and for which functions is this going to be true? And so we need to talk a little bit about path independence. Before we do that, I want to talk about what's called a reparameterization of a path. So let's say if gamma has some domain, so if gamma describes some curve and gamma of t is the equation of that curve where t goes between a and b. And if we have another parameterization, let's call it sigma, and sigma of t has values between c and d. So if gamma and sigma, if they describe the same path, if they describe the same curve or the same path, then we say that gamma is a reparameterization. So gamma is a reparameterization of sigma is a reparameterization of gamma if sigma is equal to gamma composed with some map tau, where tau is increasing in maps the interval from CD to the interval from AB. Okay, so it's kind of a very abstract idea, but the idea is actually really, it's an abstract definition. The idea is super simple. So let's just do this with an example. This is often the case in math. You have these abstract, kind of hard to hard to understand definitions, but they're precise definitions, and they're there because they're precise. But I think actually it's just easiest to talk about this with an example. Let's say that we have gamma of t, and gamma of t is going to describe the unit circle. So it's going to be e to the it, where t goes between 0 and 2 pi. So here we're going to talk about a parameterization of the unit circle. Then sigma of t, if we take this to be, say, e to the I t squared, where instead of being between 0 and 2 pi, maybe t is between 0 and the square root of 2 pi. These are going to describe the same curve. Gamma is equal to sigma composed with tau, where tau, so tau is going to be t squared. That's an increasing function, and therefore sigma is a reparameterization of gamma. Okay, so that's really all we mean when we say reparameterization, is we're parameterizing the same curve, and we're thinking of sigma as being gamma composed with tau, where tau is increasing. Okay, notice that tau maps the interval from 0 to 2 pi into the interval from 0 to the square root of 2 pi. It maps it into the interval from to 0 to 2 pi. Okay, so one thing that we can check is that if we were to integrate, say, z squared over, that's fine, over, I've already picked this. So over gamma, if we were to integrate z squared over gamma, we could use either parameterization to do this, and you can check that they're going to be equal. So on the one hand, you will get the integral from 0 to 2 pi e to the it squared times I e to the it dt, and I'll let you evaluate that. On the other hand, you could get you could go from 0 to square root of 2 pi. You'd have e to the it squared. We're going to square that function, and then the derivative of e to the it squared is going to be 2it e to the it squared dt. And it turns out that, and I'll leave this to you, just verify, just evaluate each of these, check that they're equal. They are. Okay, and so what ends up happening is So what ends up happening is, I'll call this a proposition. If sigma is a reparameterization of gamma, and if gamma is piecewise smooth and f is integrable, then the integral of f of gamma times gamma prime, in other words, the line integral over the curve, is going to be the same whether we use our curve gamma of t or sigma of t, if one's a reparameterization of the other. Okay, so in this sense, this is kind of like the first step towards talking about path independence. It doesn't matter whether you use the original parameterization or reparameterization, you'll get the same value if we're talking about the same path. Okay, so that's the first step. That's the first step that we need.